The open ocean is just one of the wildest, most powerful places on Earth. And for decades, we've been dreaming of harnessing all that immense energy. But here's the question. How do you build a power plant that can not only survive out there, but actually thrive in all that chaos? Well, the answer might just lie in a new kind of tech that's designed to literally ride the waves.
And here it is. This is the floating hybrid system. Now take a look at this thing. It's not just another wind turbine. It's a true hybrid. You've got a massive 5-megawatt turbine way up top, and then, get this, 2 powerful marine current turbines down below, capturing energy from both the wind and the sea. It's a brilliant design, but it creates this massive challenge. How in the world do you keep a towering structure like this stable and efficient when it's being pushed and pulled by forces from every single direction?
So in this explainer, we're going to break down the science behind keeping this giant steady. We'll kick things off with the fundamental problem, then we'll look at the machine itself, introduce the smart system that's designed to control it, see how it actually performs in a virtual test, and finally, we'll talk about what this all means for the future of energy.
All right, first up, the Offshore Balancing Act. And trust me, this isn't just a clever name. It's the core challenge at the heart of making any of this floating energy stuff work.
This quote right here really gets to the heart of it. For a structure this huge, even a tiny bit of tilting or rotating isn't just, an inconvenience. It's genuinely dangerous. It puts just immense stress on the entire structure, and it makes the power output swing wildly up and down, which is the last thing you want from a reliable power source. So the key number everyone's watching is something called the healing angle. And put simply, it's just a measure of how much the platform is tilting over. The goal for any floating energy system is to keep this angle as close to zero as humanly possible, no matter what the ocean decides to throw at it. Now, to really put this system through its paces, engineers modeled one of the most challenging places on Earth, the Strait of Gibraltar. And just look at these weather simulations. The wind, the currents, they are incredibly volatile, constantly shifting direction and intensity. This is the kind of unforgiving, real-world chaos that this platform has to be able to handle.
So this all creates a fundamental conflict for the engineers. They're basically chasing two opposite goals at the same time. On one hand, they have to minimize the platform's tilt to make sure it lasts a long, long time. But on the other hand, they've got to maximize the power it's generating. And a lot of the time, doing one means you have to sacrifice the other.
So what kind of machine is actually built to take on this incredible balancing act? Let's take a closer look at this hybrid power platform.
Okay, this thing is a hybrid powerhouse. It starts with a pretty well-known wind turbine, the OC3 Highwind. That's 5 megawatts right there. But then it adds 2 550-kilowatt marine current turbines just below the surface. So what that means is it's constantly pulling in power from 3 separate sources all at once. This diagram really shows you just how complex this system is. See, over on the left, you've got the inputs, wind speed and current speed. Each of those feeds into a separate controller, one for the main turbine and others for the 2 marine turbines. Then the actions of all 3 of those turbines combine to influence the floating hybrid system there in the middle, affecting its movement in pretty much every direction. It's this constant, dynamic dance of forces.
Yeah, this is way too complex for any human to manage in real time. It needs a brain. And that brings us to the real hero of our story, the smart control system.
Okay, so the technical name is a multivariable linear quadratic integral controller, or LQI controller for short. I know, that is a total mouthful. But don't worry, the idea behind it is actually incredibly smart and, well, elegant.
Probably the best way to think about it is like an expert tightrope walker, right? They're not just leaning one way or the other. They are constantly feeling for these tiny, tiny shifts in balance, processing all that information, and making thousands of small, coordinated adjustments with their arms, their legs, their core, all to stay perfectly upright. That is exactly what the LQI controller does for this platform. So here's how it works, broken down into 4 steps. First, it senses every little movement the platform makes. We're talking the side-to-side roll, the front-to-back pitch, and that twisting motion called yaw. Second, it processes all of that data at the same time. Third, it calculates the perfect rotational speed for all 3 turbines to counteract any of that unwanted movement. And finally, it executes all these little adjustments in perfect coordination.
And this diagram, this is basically the system's technical blueprint. Now, don't worry about all the labels. Just follow the flow of the arrows. That FHS model box, that's the platform's actual movement. That information flows out as an output and gets immediately fed right back into the LQI controller. This is what's called a feedback loop. The controller is constantly comparing the platform's actual state to its ideal state, which is perfect stability, and it's sending out new commands to the turbines to fix any little deviation.
So what is this brain constantly sensing? It's watching 6 key things. First, the 3 rotation angles. That's the side-to-side roll, the front-to-back pitch, and the twisting yaw. Then, it's also looking at the power being generated in real time by the wind turbine and each of the 2 marine turbines. You can think of these as its eyes and ears.
And based on everything it's sensing, what can it actually do? Well, it has 3 specific actions it can take. It can tell the wind turbine to change its speed, and it can do the exact same thing for each of the 2 marine turbines, all independently. These are its hands.
And this is really where the magic happens. You've got those 6 streams of information constantly flowing into the controller. It then makes these super fast, intelligent decisions about what to do with its 3 outputs. It's not just controlling them one by one, it's orchestrating them, making them work together as a team to find that perfect balance between staying upright and making as much power as possible. So, the theory is fantastic. But does it actually work? It's time to put this controller to the test in a simulated but very realistic environment.
So to test it, the researchers gave the controller a very specific trade-off to solve. They programmed it to prioritize the platform's stability above everything else, but with one critical rule. It was not allowed to sacrifice more than 1 megawatt of power from the main wind turbine to achieve that stability. This set up the perfect showdown, power versus stability.
Well, the results were, frankly, incredible. This chart shows the healing angle, that dangerous tilting. On the left, with the control system turned off, you see that huge bar. The platform was getting tossed around like crazy. But then, look at the bar on the right. The moment they switched the controller on, the tilt was drastically reduced. The platform became so much more stable. And what that really means is huge. Less tilt means less stress on every single bolt and beam. It means less metal fatigue. And that all adds up to a much longer, safer life for the entire power plant. It's what turns a cool idea into a durable, real-world solution.
Okay, but what about the power? There's gotta be a catch, right? Well, here's the fascinating trade-off. To get all that stability, the control system did have to sacrifice a tiny bit of energy generation. See how the bar on the right is just a little bit lower? It was intentionally slowing down the turbines at just the right moments to keep the platform stable. This wasn't a bug, it was a feature, an incredibly smart, calculated decision.
So, what does a successful test like this really mean for the bigger picture? Let's zoom out and look at the future of floating energy.
So there are a few huge takeaways here. First, this proves that getting different types of turbines to work together cooperatively is incredibly effective. Second, the controller was exceptionally good at reducing yaw, that side-to-side twisting motion. And that's a huge deal because yaw puts this uneven, grinding stress on the main turbine bearings. But most importantly, it shows that these smart control systems are the key to making these massive offshore structures last longer, which makes them way more affordable and realistic for our energy future.
So when you take a step back, what does this all mean? It really suggests that the next giant leap in renewable energy might not come from just building bigger and bigger turbines. It's going to come from building smarter, more resilient systems that can work together to thrive in the toughest places on Earth. And that kind of leaves us with one last big thought. This whole project was about teaching a system of turbines to work together for a shared goal. It really makes you wonder, what other massive challenges out there could we solve by applying that same idea of intelligent, cooperative control? If you really want to geek out on the math and the deep engineering behind all this, the full research paper is available at the link on your screen. Thanks so much for joining us for this explainer.